So, as part of celebration of the Hamilton, here at the Hamilton Mathematics Institute in Trinity College Dublin, we are very happy to welcome our friends and colleagues, Andrei Okounkov from University in New York, Columbia University, and Kapranov from University of Tokyo. And they kindly agreed to have a conversation that might interest not only participants of this conference, but generally to the audience interested in mathematics and theoretical physics. Thank you so much for agreeing on this.
Thank you for
please enjoy.
And congratulations on both this wonderful space and this very interesting conference, and really looking forward to that.
Well, of course, it's on such an occasion, I think it's natural to return to what mathematics owes to William Hamilton and his work and his influence over more than a century. It will be 2 centuries soon, and I think it has been one of the fundamental contributions to mathematics and physics. So maybe Andrei can say something about his.
Maybe before we talk about specifics, I think it's fantastic that you, especially here at Trinity, you feel really see the connection of time. Mathematics that was like you said 2 centuries old is still connected to the present day, not just in the space of ideas, but also the buildings, the portraits, the certain ways of life, and that kind of continuity. I think I find it's extremely important, because especially in today's world, where I think people are very I cannot speak for 1 minute without criticizing some people, some unspecified people, but people really maybe a little over-fixate on modern things this time. They want to somehow break with the past, and all too easily. I think in mathematics is extremely important to recognize there's certain themes, certain ideas, things build upon one another. You see the ideas of people who Hamilton and other people here at Trinity. You see how what they worked a century or 2 ago, that still continues today, and you don't have a feeling that you're born yesterday. You just have to rediscover everything for just reinvent the whole thing. You see, you're building upon a foundation that many great minds of the past built, and that I think is great to be celebrating. To be celebrating what's 220 years of since what?
Hamilton, let's say 1840s, like say 1841, I think, is his discovery of quaternions. So it's going to be 200 years.
But this is 200.
The college, of course, dates from well before.
Yeah, but I thought this is 220 since his birth, right? Or something.
Yes. So it's about this. Yes, I think that especially in mathematics, some fundamental mathematical problems have longer duration. They are eternal in a way. They are forever, and it is just the form in which they are presented. The form changes, and the problems themselves they remain. And in particular, what we know about Hamilton, the 2 greatest achievements is the theory of quaternions and Hamiltonian mechanics, which is symplectic geometry in modern terms. And in a way, they are, I would say, they are right now they are the cutting edge of modern mathematics and physics. Whenever you look, it is symplectic manifolds. Whenever you look, it is in physics, it's clearly all theories of all discussion of supersymmetry in physics. It's quaternionic, actinionic analyticity. It is, whenever we look, we see basically ideas of Hamilton in model form, and not only they are not obsolete, but they're exactly what people will study in the next, I don't know, 50 years.
Yeah. My whole life I study, well, I don't know, on and off me, not every day of my life, but somehow, more or less my whole life revolves around one algebraic symplectic manifold or another algebraic expressing manifold. Why do you think they're so important? Like, what's your answer to that?
Because I think they certainly need to explain what's happening in physics and a certain doubling. So the fundamental issue in physics is that equations are of second order. There are two levels, or if you want, there are kind of two worlds, the world of position and the world of momentum. So, and the equations are not of third order, they are of second order, always. So therefore, the ordinary dimension of space or space-time is doubled. That's how we form symplectic manifolds. But why? One can ask why why everything is of second order, and I don't think there is any satisfactory answer to that.
There's some, of course, there's some theorems that say that you have.
Yeah, no, you can make up.
Yeah.
You can write equation of any order. But there is some structure of physics, structure of nature, structure of space-time, that it is deviation from straight line, the acceleration, which is driving dynamics. If things go in straight lines, then nothing is happening. If you deviate from the straight line, that's the curvature, that's the strength, and that's the field strength. And so everything is doubled. If you want, there is this world, and this the other world, the world of kind of mental world, the world of intentions, the world of momenta, the world of our wishes, and this continuous interaction between this world and that world, which constitutes the physical development.
You know, it's funny. I obviously didn't prepare for this conversation by way of reading up on Hamilton, but I just today over lunch. One thing I had no idea that he had some work in Fourier analysis also. And that's does he know anything about it or
No, I don't know about it.
Okay, it's interesting. I don't know if he himself realized that this is what of course
No, but we know
the two
that
worlds
symplectic-
the two worlds you're describing they're related.
Fourier transforms,
Yeah,
symplectic transformations, they
Exactly.
correspond to Fourier transform. It's a part of the structure. So that's why this is such a central importance in mathematics.
But still, there's some. For instance, you know, one of your maybe favorite subjects also, geometric representations.
Yes.
You may want to consider, what's a geometric representation theory? Is that instead of matrices, you act by correspondences.
Yes.
But why is that the good correspondences always Lagrangian? If you're somehow, you have to be some kind of Lagrangian correspondences between symplectic manifolds, and not something random. Like if you want to write, you would think that this is why do we need Lagrangian? We have perfectly good correspondences, between some Grassmannians, different Grassmannians, they're natural correspondence. But you want to take like conormals of that correspondences for between cotangent bundle.
That's again, we need to bring into action that other world.
Yeah.
So other world of differential equations. So how do we pass to cotangent bundle that is sort of suggests the wave dynamics, suggestive of wave fronts, of distribution, of movement of matter, movement of radiation. So everything is connected with the wave nature of matter. So of course, we can look at the sort of at the slice of what's happening now. That's the manifold, and what can happen now and can possibly happen later. That's the cotangent bundle of the manifold. So something like that.
If you want a random question on this topic, I've been wondering on and off. Like this is of course going back to the Grassmannian. Grassmannian have important, play important roles in mathematics. In particular, that's the BU spectrum. And,
Yes.
And then related Tom spectrum, but those are not somehow. There's nothing symplectic there.
Not yet, but we can make it symplectic.
Yeah.
There are different points of view. We can start with anything and make it symplectic.
Yeah.
And there are other symplectic things that don't directly come from anything by this procedure. So there is an extra symmetry in a way that goes back to also to Sophus Lee and the idea of contact transformations. That we don't only move the points, we also move the contact elements. This is something very similar to the cotangent bundle. So again, always the idea is to reduce our differential equation to something of first order, to actual movement. So then we double the dimension in one form or the other. So, and there are structures which don't come from time slices. Let's call ordinary manifold kind of fixed time slices. And let's call symplectic manifolds something that describes dynamics. So not everything comes from straightforward time slices, because there is more symmetry. So we can glue things together, not necessarily by moving around the fixed time slices. So that's probably the most remarkable feature, the existence of other symplectic manifolds that don't come.
Oh yeah,
as
surface.
Cotangent bundle, yes. Yes, for instance, yes.
For instance, yeah.
So that's, and also, I think that the other contribution of Hamilton, which is quaternions, it's also remarkably, as the time goes, every decade after decade, it acquires more and more of importance and of central nature. Immediately after the introduction of quaternions, they were very fashionable in England. There was a school of quaternionists. Of course, there were anti-quaternionists which didn't like that. There were books written about quaternions. Then people say, oh, okay, that's just vector calculus, or this is just calculus of differential forms. But as the time went, like 50 years, 100 years, actual quaternions acquire more and more importance. For example, relating to the symplectic geometry, the compact form of the symplectic group is the quaternionic group, is the unitary group of quaternions. Algebraic topologists, when they consider, they call symplectic, symplectic cobordism. It's a cobordism theory based on group of what? Of quaternionic unitary matrices, because it's a compact group that they care about. And more recently, the supersymmetry, the hierarchy of number systems, real numbers, complex numbers, quaternions, octonions, this corresponds to the hierarchy of supersymmetry. N equals 1 supersymmetry, N equals 2 supersymmetry, N equals 4, and so on. And it ends. In physics, it's important that it ends at some point. And so quaternionic Keller manifolds correspond to like simple supersymmetry, quaternionic or hyperkeller manifold correspond to.
No. Keller is already extended.
It's already double symmetry, four-tuple symmetry, and it more or less follows this exactly. And this is the highest, the hottest subject in physics for the last 20 years, extended supersymmetry. Goes back to quaternions.
You think Hamilton had the idea that quaternions would be also so important? I mean, over like any number that you consider various quaternions, and they kind of teach you.
You mean even quaternionic algebras?
Exactly.
No, that probably he did not consider. That I think that is the later contribution of the German school of class field theory of M. Magnotta and others, quaternionic algebras. Yes, but I think Hamilton viewed his theory of as a language for physics. So to describe something which was later formalized by Maxwell equations. So the behavior, kind of interrelation of electric and magnetic field was called the curl operator, the nabla operator introduced by Hamilton, but later was all unified to a point by theory of differential forms and by Hodge theory. Yeah, but originally, I think Hamilton viewed this as a language to understand physics of our actual space-time, of dimension 4. So quaternions have dimension 4. It has one real part and three imaginary parts. It's the parts which is like space and time. So of course it's.
No, I understand that. Just this is such a common theme in today's mathematical physics is to also bring some number theory consideration. You know, wondering if Hamilton had he maybe lived long enough to see the number theoretical applications of quaternions, you think?
Well, of course he would be very happy. Yes.
I had no idea the Hamiltonian cycles or the Hamiltonian path.
Yes, that I knew the name, but I didn't know the details. Yes, it's something about graph theory.
Yeah, and specifically that was in his mind. I think it was connected with this dodecahedral.
Yes.
I forgot what was the connection with the quaternions in his mind, but I think there was some connection. Yeah.
Well, I think that's that idea that in physics what we have is a square of something else. So what we see in physics is always the square of something which is invisible and which exists but not observable. For example, the field strength is the square of the connection operator. F is nabla square.
Yeah.
Right, so F is observable, but nabla. So the connection is the field potential. It's not exactly observable. So it's a square of something, right? Also in quantum mechanics, what we observe is the square of the wave function, square of absolute value of the wave function. But the wave function itself, we don't know. So again, this is an idea of the previous level of the square root. Yeah? Anytime we do quantum mechanics, we see square roots of everything. Right? For example, in the initial object in quantum mechanics is a half form, because half forms can be multiplied to get a volume form, half density, right? And L2, and they form an L2 space. So again, this sort of two-leveledness, if you want, it's again a manifestation of this doubling of the number of variables that we see in symplectic philosophy. So from quantum mechanics point of view, we're dealing with symplectic manifolds, and the vectors are given by Lagrangian submanifolds, which are of half dimension, which are in the middle. So it's about the same.
You know much about Hamilton's work, and he has also some algebraic geometry work.
I don't know much. I think it is. Some people said that the early study of quartic surfaces, which we know like nano-Kummer surfaces, has been done by Hamilton. That's very possible. Yeah, so again, after the study of cubic surfaces by Kelly, that probably was the next one.
Which of all of this you think is somehow the most important for today's math, or for tomorrow's math, or all of them?
I think it is. I think first the symplectic philosophy, and also the philosophy of exceptional objects, exceptional groups. So things end. For example, after Hamilton and his quaternions, there was Kelly with his Kelly algebra, which sort of is, again, plays an enormous role in physics. But if you want to generalize to any number of dimensions, that was the work of Clifford with his Clifford algebras, later with spinors. How can we understand what many people spent a lot of time back in the day? How do we understand, say, complex quaternionic analyticity? Well, in modern terms, is the study of the Dirac operator. The Dirac operator exists in any number of dimensions, is constructed using the Clifford algebra and the irreducible models of the Clifford algebra. But the dimension of the corresponding irreducible models of the space of spinors, it grows exponentially. And the interesting physical life happens when this dimension is not too big. So, for example, in 2 dimensions, the space of spinor is also 2-dimensional. That's why we have theory of complex analyticity. In 4 dimensions, the space of spinors, there are 2 types of spinors. I forgot what they're called, but anyway, there are 2 types of spinors, and this calls the twistor theory. So using those 2 spinors to build a 4-dimensional space-time. There is a little more in dimensions up to 10, but after that, the dimension of the spinor spaces becomes so out of control that it's hard to account for all the components. And this also corresponds to the theorem, I think it is due to Werner Nahm, that in dimensions more than something, the supersymmetric theories don't behave very well, because there are so many components of supersymmetric fields that there cannot be reasonable physical fields to account for them. They become fields of let's say, higher spin with respect to Lorentz transformations, and we don't observe those particles of higher spin. So that's why somehow physics ends at dimensions 10 or 11, whichever you like more, but that is more or less the end. So the idea of physics somehow is that it's interesting to look at things at their end. So it's not in the process of going forever. No physicist wants to go forever. Physicists want to be somewhere where it's exceptional coincidences between one thing that goes forever and another thing that goes forever. For example, the group SU2 and the group SO3, so parts of 2 large families, and this part, there is coincidence. And then physics begins. But even for SU1000 and SO1000, they are unrelated, and there is no physics yet. Why is this? We don't know. It's some kind of mystery. In general, in physics, it's even more mysterious than mathematics, because there are some principles, and the principles, they don't have a logical explanation. So what I said can be viewed as a principle in physics, but why is it so? We don't know. Or for instance, there is a principle of least action. What's the explanation of the principle of the least action in physics? By the way, it's also associated with the name of Hamilton. So I think the idea goes
to rewrite the
yes, all the equations of motion are written in this form. This is, by the way, another contribution of Hamilton, even though the idea of that we live in the best possible world goes back probably at least to Leibniz. Yes.
But the modern idea is not that, I don't know if it's modern or not, but the idea is not that the best world, it's just in the path integral. Everything else is kind of
yes, no, even more so. That this idea of the best possible world somehow matches the incredibly sophisticated mathematical framework of path integral e to the is. So it's even more mysterious. It's one thing to say.
No, but that I think is easier to explain. Is that everything, so to speak, everything contributes, and it contributes equally. It's just the direction of the contributions.
Yes. So it's even more grounded. This principle becomes even more grounded by how unexpected each physical development is. So we think that this thing should explain physics, and turns out it's something else. Is explaining it. And each time it is a surprise. It's impossible, I think, to have, like they say, a 5-year plan like they had in Soviet Union. Yes.
Yes. Oh, okay. My metaphor for this is that there's this famous quote about Galileo, about the book of the universe and how it's written in the language of mathematics.
Yes, of course. Yes.
But my metaphor for that is that every chapter of that book is in fact written in a new language. I mean, it's very difficult to predict what's the. Of course, the later chapter, you can interpret the previous language in the chapter in the language. So there's you can interpret previous releases of that language in terms of the language of the latter chapter. But it's extremely hard to know what would be the language. What would be the language that would be required in the next chapter? In that sense, it's absolutely amazing that Hamiltonian mechanics is 200 years later still extremely relevant, and in terms of not just in some kind of spirit, but actual language.
Yes.
Because if you look at the language in which, for instance, Maxwell writes.
Yes. You mean the original form of Maxwell equation?
Exactly.
Of rotor and divergence of gradients.
It's just in general. It's just the fact that I think Hamilton kind of stands out in the way that he's. I never tried to read his original papers, but in terms of just the kind of the basic basic contribution that we discussed there. They're
very clear, I think.
Very clear today, as so to speak, as understandable and as relevant.
Yeah, but that maybe that's the secret to strive for the clarity. By the way, another thing occurred to me: the Hamilton-Kelly theorem about the matrices. That every matrix satisfies its own characteristic equation. It's known as the Hamilton-Kelly theorem. Yes. Again, so. Very clear statement.
What was the relation between Hamilton and Kelly? Who was
probably at the similar time. Yes, early papers of Kelly, it's 1840s. I remember reading some of them. Yes.
Was he was a little older than Hamilton, or the other way around? Or?
So I don't remember exactly. Approximately the same generation, I think. Maybe a little older, but approximately the same generation. So the language changes, but the problems remain. And it's, of course, we want to somehow guess the language of the future. I don't know if it's possible. Maybe, because if you try to impose your language on the future, it usually doesn't work. If you try to impose your language, all attempt to impose a unified system on mathematics, somehow it didn't work. And that's interesting. It's interesting to speculate why.
I don't think you can discuss the successes and failures of any kind of unification, but I think something else it's not just the language. Is in math you very often realize that sometimes quickly, sometimes after years of barking up the wrong trees, you realize that the problem is just not. You weren't asking the right question. You somehow you weren't looking at the problem from the right angle.
Yes.
It's about something else entirely. Yes. It's like sometimes I don't know, in a crime drama you'd think that this you think that this is the plot, but in fact something completely different is happening, and that
somehow presupposes it suggests the idea of the right approach, and this is one of the things that I think mathematics teaches us, the idea of somehow the fundamentally right approach. And that very often just striving for the right approach actually helps. You can, as you say, bark up the wrong tree or going into some dead-end direction and put an enormous amount of work, and then just to change things a little, and it fits into places. So that's remarkable.
I think that in fact this is the fact that we sort of look for that and accept it. So it's not like we, if somebody sees the right approach, people just accept it, right? We're not trying to I think that's
sometimes it's clear.
accepted and adopted. Yeah, sometimes
if it's right, so it becomes clear.
Exactly.
So there is no argument.
Exactly.
Yeah.
And I think that kind of helps. That I think also helps to make this sort of this connection through time. I think it makes it more streamlined in a way that the actual trajectory of research, of course, the actual trajectory of research might be some kind of piano curve.
Yeah.
But we backtrack and we look for what's the right angle, what's the actual right thing, and then in that space of, I mean, if you look the total space of ideas, they turn out to be not that far away, and so then you can follow that path. You don't have to. I mean, it's not like you have to read everything that was written between now. You can
yes, exactly. You can trace.
You can really feel that connection because it's in the 200. Of course, a lot of research was done in 200 years, but we not only did research, we also compressed it to something you can really see.